Our third and final video of 12.4 and for the chapter, we're going to talk about point of discontinuity. And that happens when a rational function has a common variable in both the numerator and the denominator. And what happens is this creates a hole in the graph. And you'll see what I mean once we start looking at a couple examples. We're going to take number 8 first. We have the function f of x equals x squared plus 2x minus 3 over x minus 1. I'm going to take this, I'm going to put it in decimals so we can just take a look at what happens at the graph. So if you look at this graph, you'll notice that it looks like a linear line. And if I zoom out, you'll see that it is a linear line. And there's no asymptotes, even though it's clearly a rational function. But if we zoom in and I look specifically at the number 1, so number 1, and I go up to 4, I click on it, you'll see that the y value is undefined. And you'll also, if you can see underneath my mouse, it's an open circle there. Whereas when I scroll down, it's a filled in purple circle. But at 1 and 4, it's an open circle and it's listed as 1 comma undefined. Now, if you look at the equation, the 1 part will make sense because when I put in 1 into the denominator, that denominator is 0. But why does it create then this linear line? That happens because if we take the numerator and we factor in the numerator to x plus 3 and x minus 1, you'll see that the factors in the numerator and in the denominator are the same. That's what it means by common variable factor. And they cancel each other out. So f of x reduces to x plus 3. But as we know in the original, you can't have x be 1 because the 0 would be in the denominator. So the hole occurs, oops, at x equals 1. So what we're going to do is now we're going to take the new function, f of 1, and we substitute in 1 for x, 1 plus 3. So when f equals 1, the output is 4. This is where the hole occurs, at the point 1 comma 4. So I will put a hole, 1, 2, 3, 4, at this coordinate point 1, 4. And what I'm going to do is I'm going to graph the rest of this function, x plus 3. And we do that just normal, like a linear line. So I do y-intercept, and I go up 1 over 1. That's my hole, so I'm not going to plot on it. And I keep going. Slope of 1, or I could go down. And I'm going to connect the dots to make it a continuous linear line, except again, we have this hole. I know in your packets it shows a word problem, but we're going to focus in on the graphs for this chapter and kind of skip over those for now. I want you to pause the video, and I would like you to do number 9, where it says f of x equals x squared minus 9 over the quantity x plus 3. I'd like you to find the hole in the graph and then eventually graph it. When you're done, resume the video and see if yours matches mine. You can see the hole in the graph occurs at -3, -6. The function reduced to x minus 3, so the y-intercept was at -3 with a slope of 1. Before we finish this video, I want to talk about 3 quick things that we talked about in video 1 of this section, and that has to do with the asymptotes and when they occur. I want to make sure we know when certain asymptotes happen because that will make figuring out the graphs faster and easier. So the first thing is, and I'm going to do this backwards than what's written, when the degree is higher in the denominator, what's going to happen is there is going to be a horizontal asymptote at the x-axis, or y equals 0. So this will save us time again, because if as soon as I see that I have a higher degree, doesn't matter the other numbers, but as soon as I see a higher degree in the denominator, I automatically know there will be a horizontal asymptote at y equals 0. The next thing says that when the degree is the same, I'm going to have a horizontal asymptote again, but it's going to be at a different number. So again, I want to make sure that we can look at these and make sure we understand them quickly. So if I had something like 5x minus 3 over 2x plus 5, the degrees are the same. And in the first video, we talked about how x approaches infinity and what happens to the numbers, and then reduced it from there. But a real simple way is those numbers really don't matter. What's going to matter is this right here, the 5 over 2. So when the degree is the same, we can really look at that ratio right here, and right away we can see that that asymptote is 5/2 without doing very minimal work. And finally, a slant asymptote occurs when the degree is higher in the numerator. So again, if f of x equals 3x squared plus 4 over x minus 1, the degree is higher here, so we know that a slant asymptote is going to occur. To calculate the slant asymptote, you need to do synthetic division. And you would take whatever equals 0, so I'd put 1 there, and then I'd use those coefficients, and I drop that down, and I get 7. And remember, we don't care about that remainder right there. This 3x plus 3, that's our slant asymptote. So we use those numbers with the slope and the intercept to work.